right, we're going to go ahead and finish up this chapter today because we have Dr. Compton's coming in today, and I don't know how much time we'll have in class, so I'm going to make a video covering all the rest of it from where we left off in class. We had gotten to the junction rule where we talked about basically through conservation of charge, the amount of current that goes into a junction has to be a total of 0. So you'd count, this one as positive going in and these two as negative going out, and you add them up and they have to equal 0. And then we also talked about how you basically sometimes just have to guess which direction you think the current is going. If you guess it wrong, then when you work the problem out and solve for the current, you'll just end up with a negative sign, in which case you would know that you just picked the wrong direction. You don't have to change anything else about it or rework the problem. You just know that the current was going the other way. All right, and then so you fix your picture, flip it around, and adjust for it accordingly. All right, next we have the loop rule, and the basic idea is that the potential drop around any closed loop must be 0. It has to kind of return to its starting point, and I was kind of hinting at this a little bit in class. So if this is, you could kind of say like, oh, let's say this is 12 volts here, so it's like a plus 12 volts we get here, which means that carries this whole way around and stays plus 12 volts over here. But then it has to go through the resistor. And when it goes through the resistor, there's a voltage drop. In this case, there's only one resistor. This has to be 0 volts over here. So we have to have a 12 volt drop across that resistor. And then this goes down to 0 volts right there. Okay. And that basically, if we go through and add these all up, we should get a 0 here. So let me put a negative right there. This is the voltage drop on that one. And so what I mean by that is, so you pick a point on your circuit or a node or something. So let's say we start right here. We're going to go plus 12 going up the battery from negative to positive. It's like we're going up the incline. So a plus 12 for that. Okay, so plus 12 volts for the battery from that EMF. And then we're going to come around here over to the resistor side, and we're going to drop down 12 volts. So minus 12 volts, and then that equals 0. And so, And so basically that's essentially how the loop rule works, and you can do it around any closed loop, even adding in more and more things. You do, and you could also do it the other way. You could have gone counterclockwise and said this is going from positive to negative on a battery. That's a drop of 12 volts, and then coming around here, this would be going the opposite direction of current, and so it would be actually an increase, like swimming upstream up the river, going against the current here. It would be an increase, or swimming up the waterfall maybe. It would be an increase in 12 volts, so it would have been like minus 12 volts plus 12 volts, like that equals 0. And this is useful when you don't know, for example, how much current is flowing through this. You can combine this with Ohm's law, and it helps you start to solve these things. All right, so Kirchhoff's rules. One, the variables for which you're solving for are the currents through the resistors. You need as many independent equations as you have variables to solve for. So sometimes you can get more independent equations than you have variables to solve for, but you need at least as many. So if you have 3 different places where there's 3 different currents, then you're going to need 3 different equations. And you're going to end up needing both the junction and the loop rules to do this. So let's take a look here. In the circuit below, what is the current through R1? So for this one, we could go through and we could combine these into one resistor, do Ohm's law, do all that kind of stuff, or we could take advantage of the loop rule. So for example, I could say right here that, this is the negative side, this is the plus side, so this is a plus 10 volts. That's a plus 10 volts going this way across the battery, which leads us up to here. So this is I1. We'll call this I2, and we'll call this I3. Maybe I need to actually change this one to I3. We'll call that I3, so that I1 is actually going through R1, like that. and we'll say that this direction is the current is that way. So now I've labeled directions, everything like that. So I've gone up a 10 volts over the battery. Now I come up here and I'm going to go to the left. I'm going to come through this one in the direction that the current is. So that means I'm like going down the waterfall. So that has to be a minus, and then this is going to be, remember, V equals IR, so it has to be minus whatever the voltage drop is. So it's going to be I1 times R. This is V from Ohm's law, right? So V equals IR, like that. And that has to equal 0, because now after that, I'm back around where I started. So this is my loop rule. I went in this direction around the loop and got that equation. Now, if you look at that equation, I only have one unknown. I know what R is, so I should be able to go ahead and solve this. So I1 is going to equal, oh, and this should be an R1, is going to equal 10 volts divided by R1, which is just going to be 10 volts divided by 5 ohms, which will be 2 amps. So that should be our answer there, 2 amps. Now, again, we could have done this in a different way. We could have reduced the circuit and stuff like that, but I just wanted to show you me applying at least one of the loop rules right there for a simple example. Okay, so 2 amps. All right. Oh, and another way you can think of it is you have to remember these both have a 10 volt drop across them, which is what we ended up doing anyway. With V equals IR, it would have been 10 volts equals IR, so it would have even given us the same little equation as right there. Okay, so how about this one? The points P and Q are connected to a battery of fixed voltage. As more resistors are added to the parallel circuit, what happens to the total current? So we're adding them in parallel, and if you remember, adding resistors in parallel, we do that with the equivalent resistance is equal to the sum of the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the resistances that you're adding up. And so if we're just adding a bunch of these up like this, every time we put a new one on, we are decreasing the total resistance. And if we decrease the total resistance, then the total current is going to increase. Okay, if you keep adding more. If we were adding them in series, right, if we kept adding, you know, here's one resistor, and then we kept adding another one, and then another one, and then another one, and we kept adding them in series, we would decrease the total current because there the resistors add up, right? For series, it's R equivalent is equal to R1 plus R2 plus all of them. So that increases resistance, but here, parallel decreases the total resistance. Yeah. So next one, current flows through a light bulb. If a wire is now connected across the bulb, what happens? So essentially, we've given this now what is called a short. We've given it a path that it can flow through the current with zero resistance, which means the majority of, when two things are in parallel like that, two objects are in parallel, the majority of the current's going to go through the thing with the smallest resistance, which automatically tells us that most of the current's going to go up here. And if we think about it a little further, this is basically like a 0 ohm resistor, which means there's no resistance to it. As much current can flow through there as I want. So all the current basically is going to say, hey, I'm going to take this path of least resistance, and all of the current is going to go through that little shorted jumper wire, and the light bulb will then turn off. So basically all the current flows through the wire, none of it goes through the light bulb. So your light bulb would turn off. And it's a short, that's what that's called. You shorted out the circuit so that there's a easier path to go through than through the actual light bulb itself. Two light bulbs, A and B, are connected in series to a constant voltage source. When a wire is connected across bulb B, bulb A will, so if we look at this right now, with this being open, so if that's open, then these two light bulbs are in series, and they both act like resistors, because there's something in the way that's essentially what they do, which means their resistances add up, which is a total reduction in current then for the same given voltage, right? So V equals IR, so this is like our total, right, if we did an equivalent circuit. So as R goes up, current's going to go down such that the voltage of the battery stays the same. That's basically a constant. That's what batteries are designed to do. If we now go up here and close this circuit, we close it and we think back to the previous example, that means that none of the current is going to flow through B. Any of the current that comes out is no longer going to go through B. It's going to come up and it's going to go this way. It's going to totally skip B, as though B is not even there now. And when it does that, it basically means that B's resistance is no longer added on to A's, and the only thing the current has to go through is A, but it now has the full voltage to push through A. It's not split between A and B anymore, and so it should glow brighter, okay? So bulb A will grow brighter. It's getting more of the current going through it now. I guess it could be E if it was enough current to break it. I don't know, maybe. All right, so continuing on. The light bulbs in the circuits below are identical with the same resistance R. Which circuit produces more light? So if we think about this, okay, this is 12 volts, and for anything in parallel, this is going to have a 12 volt drop across it, and this is going to have a 12 volt drop across it. They're both going to have it because this is our plus 12. Let me zoom in, might make it a little easier. This is our plus 12, this is our 0 volts over here. So they each have a plus 12 over to 0 and a plus 12 over to 0, like that. So they each get 12 volt drops across them, which means they each get, for their individual resistances, they get a certain amount of current through it, right? So I equals V over R. Over here, however, this is 12 volts, so this has to be our little plus 12 over here, and this has to be our 0 over here, right? Because this is the plus 12, and this is the 0 volts over here, which means we actually have to step down twice. So if they are the same, that means that right over here, we have to lose half of it. That means in the middle is 6 volts, which means this one is only going to have a drop of 6 volts, and this one's only going to have a drop of 6 volts. And so I is going to equal V over R again, but this time V has gone down for each of them. They're each only getting 6 volts, which is going to then reduce the total current through both of them, and therefore produce less light than circuit 1. So circuit 1 will produce more light. They're in parallel. In fact, this is typically how your houses and a lot of string lights used to be like the one that's in series there, and then if one bulb burns out, the whole line goes out because now there's nowhere for it to go. But now they make like the Christmas tree string lights more like that, or at least half and half, so that the whole thing doesn't go out if one bulb burns out. And your house is also wired up like this. That way, if you plug a bunch of stuff in, it doesn't necessarily make it go, everything starts, getting half as bright as it used to be and getting dimmer and dimmer as you turn more lights on. They're like that. Okay. The 3 light bulbs in the circuit all have the same resistance, 1 ohm. By how much is the brightness of bulb B greater or smaller than the brightness of bulb A? So if we look at this, we can think about this again. This is going to have 10 volts over here. So, right, this is our 10 volts. This is our 0 volts. Let me zoom in. This is our 10 volts. That's our 0 volts. That means we have a plus 10 volts here and a plus 10 volts here, right? Plus 10, plus 10. And then it's 0 volts over here, 0 volts over here, because everywhere touching this wire, as long as we don't cross some sort of component in our circuit, it's all going to have the same voltage because the wires have no resistance, which means over here we have to drop it. So right in between has to be 5 volts because B and C are the same light bulb, so they're going to just split it in half, and they're going to each get half the voltage. That means light bulb A is getting 10 volts on it, and light bulb B, so this has a 10 volt drop on it, this has a 5 to 0, a 5 volt drop on it. This has a 10 to 5, a 5-volt drop on it. So that's what the voltage drop is on each of them, which tells us immediately that A has a bigger voltage drop across it, which, as we were just looking on the previous one, where we used V equals IR, that told us that I, which is going to be how much, or I guess we could look at it with P equals VI, since they're asking about it. They're giving a hint of power. P equals VI. We can go in here and see that, well, I guess we need V equals IR, so I is V over R. So this is just, so V equals IR, I is V over R, and I'm going to sub that in there. So this is going to be V squared over R for power. And if you look at that, we can see that as the voltage goes up, the power is going to go up, right? For the same resistance of each one of these, because both A and B have the same resistance. It's just that A has twice as much voltage. And of course, if we're squaring something that's twice as big, we end up getting something that's 4 times bigger, which means we should have 4 times the amount of power going through A than through B, which means that, what are they asking? How much brighter? So A is 4 times brighter than B, which makes B 1/4 as much as A. Okay? Yeah, there you go. What happens to the voltage across the resistor R1 when the switch is closed? So what's going to happen here is when it's first open, we have only 2 resistors that are in series with each other, R1 and R3. Everything that goes through R1 must also go through R3. And so those 2 are in series with each other, which means the voltage is going to just split between the 2 of them if they are the same, assuming those 2 resistors are the same. But whatever it is, it's going to split somehow between them, where their total voltage drop is going to add up to be whatever this battery voltage is. All right? If we close this circuit, so let's say we come in here and we close this circuit, well, now all of a sudden, when we do that, these 2 resistors are now in parallel with each other, because any current that goes through this one around the battery absolutely does not go through the other one. Okay, and that happens both forward and backwards. Like, it's a split. It either goes through one or the other. It can't go through both. So these 2 are now in parallel, which means we can add their resistances together. And when resistors are added in parallel, we get a reduced resistance. So the combined R2 and R3 is actually less than the resistance of R3 was. If that is the case, that means that their total resistance being less means they're going to use up less of this total voltage over here. All right, but we still have to have all of it used up. So this one now will use up whatever extra is left over. So if these were all the same, say this was 10 volts here, and the switch was open, and this was taking 5 volts, and this was taking 5 volts, and then we added them together, and whatever R2 is, I don't know what it is, but let's say it makes it such that both of these each take 3 volts now. So 3 volts, they're in parallel, so those volts count together around any one single closed loop. That means that R1 now has to take up 7 volts to get the total to be 10 around that closed loop, or even 10 around that closed loop right there. Okay, it has to be 10. So this would bump up to 7, which would increase the voltage in R1. Okay. What happens to the voltage across the resistor R4 when the switch is closed? Okay, so here's R4 over here. At first, R4 is in parallel with R3. It reduces their circuit, but that doesn't matter. What happens is we're going to add an R2 in here, and R2 is going to reduce the total resistance, the total combined resistance of those 3, meaning that they're going to take up less of the voltage together. Since they are in parallel, they all have the same voltage, and since they're now taking up less voltage, there's a smaller voltage drop on R4, like in the previous one, where R1's going to go up in voltage drop. R4 is going to go down in voltage drop. So is R3, and R2 is now going to have a voltage drop, which it didn't have previously. So decreases in that one. Got to just be sure to remember that the voltage drop across series is different, but the voltage drop across parallel resistors is the same. All right, which resistor has the greatest current going through it? Assume that all the resistors are equal. So R1, R2, R3, R4, R5, they're all the same. So let's look at the first part. So current's going to come out of here. There's current, and it's going to split. And here it's going to split evenly. Half's going to go through R1, half's going to go through R2 because they are both the same resistance, and it's like having two identical sized pipes that water is flowing to, and it's going to split off between them, and it's going to just split equally. But it's going to combine, so then it comes back together and combines back to being I1. But now it's going to split again, okay? But the top part has two of these resistors in series, which means that this upper path has a greater resistance, right? A greater resistance. R3 plus R4 is greater than R5. So it has a greater resistance. And then in that case, this is going to have the majority of the current going through it, more than half. And this is going to have a tiny little bit. So over here, it was like 1/2 I, 1/2 I, and then they combine back together. Over here, it's greater than 1/2 I, and it's got to then be less than 1/2 of that total current. I don't know why I put a 1 there. All right, because that R5, that path has less resistance than the other. Therefore, right, which resistor has the most current going through it? That's going to be R5. Okay. Continuing on, an ammeter A is connected between points A and B. Ammeters tell you basically how much current is going through something in the circuit, which of the four resistors, in which the four resistors are identical. So the question is, how much current is going through this ammeter? Ammeters are designed such as that they have very little resistance, or basically have no resistance whatsoever. So we might as well just call this a straight closed line and ask ourselves how much current is going to flow through that wire. Well, if we take a look at our voltage drops, we're bringing whatever this plus voltage is, whatever the voltage is right here. So why don't we say that this is 12 volts. So this is plus 12, and this is 0 over here. So as we bring this around, this is going to have a plus 12, this is going to have a plus 12. Now both of these resistors are the same, and both paths are the same. So this has to be 0 volts over here, getting over to this side, connected over to this, right? That's 0 volts over there. And all four of these resistors are the same, which means they each have to have the same voltage drop. So that makes, in between here, 6 volts here and 6 volts here. And so the question is, how much current is going to want to travel through this center line between a 6 volt and a 6 volt potential difference? And the idea is that the voltage difference between these two is 0. So it's 0, which means it has absolutely no potential to push any of the charge through that center wire, because the voltages are the same at both ends of it, and therefore the total current through that center wire, through the ammeter, is going to be 0. No difference in voltage, no potential difference, then no current's going to flow between those 2 points. Okay, so 0. All right, take a look at this one. Which of the equations is valid for the circuit below? So here we have a bunch of batteries, and then we have a bunch of resistors in there, and they even labeled the currents for us, which is nice. So we can just use the directions they gave us. So let's start by doing, well, this looks like all they did was the current rules. So if we look at this, we have I2 going up, which means if we follow that backwards, that means I2 is leaving that node. I3, as we follow it around to the left, is going into that node, and I1 is going into that node like that. So that's what we have going on right there. You could do this node up here, but it'll ultimately give you the exact same thing. It'll just be I2 going in, right? And we can try that. You can see I2 going in, but then you'd have I1 coming out over here, because over here, this has to be the same current. There's nothing to change it. So, and then over here, I3 has to be coming out. So you could use either one of these nodes, and you'll basically get the same answer, and that is add these all up so that they equal 0. So if we just look at this bottom one, no particular reason why I picked the bottom one, just I guess I did it first. So going into that node is I1, I2 is going out, so it's a minus, and I3 is going in, so that equals, yeah, so that has to then equal 0. So that right there is our node rule. That gets us a nice equation. I'm going to get rid of that one on the top. Well, maybe I shouldn't. Leave it there in case you want to see it. So that gets us that right there. And now we have to simply try and find if there's any of these equations that fit that. I1 minus I2 plus I3. Doesn't look like any of those fit this, so we might need to move on to the voltage, the loop rules. All right, so because we're leaving, what are they leaving in here? I probably should have looked at what they were trying to get first, huh? I1, I2, I1, I2, I3, I1, I2, 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 3, 1, 3. So maybe we can try a voltage drop, and so let's pick a loop. We actually have 3 loops here. The first loop can be this loop right here. The second loop can be this loop right here, and the third loop can be this greater outer big loop. The total voltage drop around all 3 of those must be 0. So let's try coming up with something for that. So let's go ahead and let's pick a starting point. Let's say we're going to start right here, and we're going to do this little loop, and we're going to go in a counterclockwise direction. So the first thing I'm going to do is bump up 2 volts there by stepping up that battery. So that's a plus 2 volts. Then I'm going to come around here to the right, and I'm going through this resistor right here. Okay, and I'm going in the direction of current I1, which means that's going to be a drop in voltage, because remember, positive charges flow from high voltage to low voltage, so that's got to be a drop in voltage. It's going down, down the waterfall. So this is going to have to be a minus the voltage there, so V through whatever that one is, which is just going to be I1 times the 1 ohm. All right, that's that resistor. After that, we're going to move up through here, and we're going backwards across a battery, which means that we're going from the high side, right? This is the plus side, this is the minus side. We're going from the high side to the low side. That means we're going to have a minus 4 volt drop right there. And then we're coming up and going through this resistor here, which is in the same direction as the current I2. So I2 is going that way. We're going in the direction of the current, so that's got to be another minus. So a minus I2 times 2 ohms, and then that has to equal 0. So that's our total voltage drop around that loop, right? So whatever that is, that's that voltage drop. And then we might as well come over here and let's do this one. We'll go around this way again, and why not, we'll start right here, and we'll go in the direction that I've indicated. So as we do that, we're going to start right up here, and we're going to go through this resistor. Now this time we're going the opposite direction of the current, which means we're basically fighting our way uphill. So this is plus I3 times 1 ohm, since that's a 1 ohm resistor. And then as we come around, we go over here, and we're going the opposite direction again of the current, the opposite direction that I2 is pointed, and therefore we're going uphill again. So plus I2 and then 2 ohms. And then we're coming along to the battery, and we're going from the negative side to the positive side, which means we are having an increase in voltage. We're jumping up. So this is another plus 4 volts, just the voltage or the EMF of that battery. Then we're coming around, and we have to go through this resistor, again, in the opposite direction that the current is going, right? Current's going that way, we're stepping up that way, which means we are again going uphill. So this is a plus I3 times 3 ohms here. And then lastly, this one over here, we're going now back across the battery to get where we started. Here we're going from the positive side to the negative side, which means we have a voltage drop there of minus 6 volts equals 0. All right, so essentially what you can do then from this point is start combining these to see. I'm basically out of room, and I think this video is going to get pretty long if I keep doing it. But what I will do is I'll add a page into this in the notes, and I'll finish working this one out so you can look at it. But essentially at this point, all you need to do is go through and combine these and see which one of these ends up being correct. You should be able to solve for them. You have 3 unknowns, 3 equations, so you don't know I1, I2, and I3, and you got 3 independent equations. So use whatever your favorite method is, solve for one of them, substitute in the others, whatever you want to do. The matrix method, add them together to get stuff to cancel out, whatever it is you're going to do that, solve for it, at least one of them it looks like, and then combine them up here. So it looks like you probably want to eliminate, well, no, this one only has I1 and I3. So, all right, give it a try, and I'll put a page in here when I actually finish that one up, and I'll try to skip this next page real quick so we don't see the answer too well, although you probably could pause it and find it. So let's move on to capacitors. Capacitors can also be connected in series or in parallel, just like resistors could. When capacitors are connected in parallel, the potential difference across each one is the same. So just like in series, whatever this plus E is, this is 0 over here, we'll say, these are each going to have that plus E, that plus epsilon, and then 0 volts over here. They're all going to have the same voltage drop across them, which means that if their capacitances are different, they're all going to have different charges that store up on them because they all have the same voltage but different capacitance. And remember, capacitance is charge per volt. So if they have a different capacitance and the same volt, then Q is equal to CV. They're each going to have a different total charge on them. So just like the resistors in parallel, they can have a different amount of current flowing through them, but they all have the same voltage. Here, the capacitors have all the same voltage, but they each have different charge. It's just that eventually it's not moving charge anymore because they fill up. And then we can make an equivalent resistor out of these ones. Now, the rule for adding these up to get the equivalent resistance is actually flip-flopped from that of resistors. In resistors, when we added them up in parallel, we added up the reciprocals. It turns out when you add a bunch of capacitors in parallel, they actually just add up. Their capacitances just add up like the resistors in series did. So resistors in series gives you a total greater resistance. Capacitors in parallel gives you a total greater capacitance. So the capacitance, as you add them like this, they can each start holding more and more charge. It's like filling up multiple water balloons. You get more and more water stored in them. It increases that total capacitance, and you get more and more of it, and you just add them up, and it's going to be greater than any one of them by itself would be. All right, and our unit here, of course, still is the farad. Capacitors in series, on the other hand, they are going to have different potential differences across them. We're going to have different voltage drops across them because they're going to, whatever this is going to be split up between them to total that, because our loop rules still work. It has to be split up amongst them, but they all are going to carry the same charge. Just like resistors in series, they all have the same current going through them. capacitors in series all have the same total charge on them, or the charge stored on them. So the total potential difference is the sum of all the potential differences across them. So this might be V1, V2, V3, and then we'd have to say that whatever our EMF is equal to V1 plus V2 plus V3, like that. Here, to find the equivalent resistance here, since this decreases the voltage on each one of these, this is actually going to result in an overall lessening of the total capacitance, and therefore a lessening of the total charge we can store on them. And so the equivalent resistor here actually adds up like parallel series resistors added up. So when we added resistors in parallel, it decreased their overall resistance. Here, if we add capacitors in series, it decreases their overall capacitance, and you add up the reciprocals like that. All right, so be careful with that, and also be careful that this is not the capacitance, it's the reciprocal of the capacitance. So be very careful of that. But yeah, capacitors in series combine like resistors in parallel and vice versa. All right, what is the equivalent capacitance of C equivalent of the combination below? So if we look here first, we see these two capacitors are in series, which means we can add them up and we'll get a new circuit where this is C and this will be, I don't know, what do we want to call that? Well, we'll figure it out in terms of C. So this will be, let's call it C1, I guess. And so 1 over C1 is going to equal 1 over C plus 1 over C, which is 2 over C, which means C1 is equal to 1/2 C. So this will be 1/2 C. So adding two identical capacitors in series like that is going to cut their capacitance in half. And then we go ahead and we try to reduce this one. In this one, these two capacitors are now in parallel, so we simply have to add them up. So to get the total equivalent resistance, so that would drop us down to just one capacitor, the equivalent one. That's just going to be C plus 1/2 C, which is, 2C over 2 plus C over 2, which is going to be 3C over 2. And so the total equivalent capacitance is going to be this 3/2 of C right there. Okay. And again, if you need to go back and look at any of these, please do. Don't forget you have a pause button. Slow down, listen to it again, rewind. All right, how does the voltage V1 across the first capacitor C1 compare to the voltage V2 across the second capacitor C2? So if we look here, we know that the combination of these two is going to be in parallel with this one, which means that the combination of those two is going to have the same 10-volt drop across it that both of these have. Another way we could think about that is say, all right, this is our 10 over here. Let me zoom in. All right, this is our 10 on this side. This is our 0 on this side. If we come around, we bring this 10 with us. And so it's 10 volts here and 10 volts here. And then we bring the 0 around, and it's 0 volts here and 0 volts here. Bring it over to there too. Okay, so bring those around, and that means those were our voltages there. Now, we have to do something here. This is 10 volts, this is 0 volts. We have to cross two things. That means that since these both have the same capacitance, they're each going to take half. That means this has to be a 5 volt in the middle here. So if we look at this, we can see that capacitance 1 has 10 volts, a 10 volt drop across it. But capacitor 2 only has a 5 volt drop across it. And since it has a 5 volt drop instead of a 10 volt, it's going to get less total charge on it. It's going to have less voltage on it, which means that this is V1, this is V2. So V1 is greater than V2. The other way you could have looked at this is just by recognizing these are in series, and so they're just going to have to split the voltage, and their total voltage has to be the same as this one, which is what I was saying when we make an equivalent. And so somehow it has to be split. They're splitting that 10 volts. This capacitor gets all the 10 volts to itself. These two have to share the 10 volts. And so it ends up getting less of it. All right. How does the charge Q1 on the first capacitor compare to the charge Q2 on the second? And for this one, since we just found that C1 has a bigger voltage drop across it than C2, that means that it's going to be able to store more charge on it. Because remember, capacitance is charge per volt. And so the total charge is capacitance times voltage. And they both have the same capacitance. It's just that one of them has a bigger voltage than the other. The bigger voltage is going to give us a bigger Q, which means Q1 is going to be bigger than Q2. You may be asking, how does the charge on C2 and C3 compare? Well, they're in series, so if we were just looking at those two would have the same charge, both less than what C1 gets. All right. Next, we can combine these resistors and capacitors in one. In a circuit containing only batteries, capacitors, charge appears almost instantaneously on the capacitors when the circuit is connected. However, if the circuit contains resistors as well, this is not the case. The resistors slow down that current. All right. If you don't have any capacitor on there and you close that circuit, there is nothing that slows any of that current, which is just moving charge, from going over and filling up that capacitor. If you add a resistor, though, this resistor takes some of the voltage drop off of here. So when you first flip the switch, this is going, assuming this capacitor is empty, it's like a totally empty water balloon, there's no water in it, this guy is going to get all the voltage drop. He's going to get the entire whatever the battery is. And this guy's going to get nothing because he's basically empty and there's no resistance to putting charge onto an empty capacitor, just like there's no resistance to putting water into an empty balloon. The first bit of water that goes in there has nothing in its way. It just goes right in easily. So this would have 0 volts at first. However, what's going to happen is this capacitor is going to start to fill up. And as it fills up, it's going to get harder and harder to push more charge on there. So what's going to happen is that this 0 volts here is going to stop being 0 volts, and the voltage drop here is going to start to rise. And it's going to keep rising until the capacitor is full and we can't add anything into it with our battery. Our battery is not strong enough to push any more charge onto it. We could push more charge onto it if we put a stronger battery there, but assuming this battery is going to stay the same, this thing is going to get filled. And when it gets filled, it's now going to take up all of the voltage. It's going to get all of it. And the resistor, because the battery or the capacitor is now full, now there's no current. Remember, V equals IR. And if I goes to 0, then the voltage drop across the resistor is now going to equal 0. All right? So as the capacitor fills, they're going to flip-flop. When you first close the circuit, the resistor has all the voltage on it, and the capacitor basically acts like a short, like it's not even there. And then as the capacitor fills up, it takes up more and more of that voltage, which means less and less current can flow through because it gets harder and harder to push charge onto that capacitor, which means it slows down. It's basically its resistance starts going up until it gets to the point that the capacitor is full, in which case it has taken now all of the voltage from it and it has stopped all the current, so there's no current through the resistor, which means now there's no voltage drop across the resistor, which means again that the capacitor has the entire voltage drop from the battery on it at that point. Okay, this can be modeled through an equation like this. We're not going to go through calculating this because again, well, not again, it says it right there, but you have to do it with calculus. So the charge as a function of time is equal to the capacitance times the EMF, right? Capacitance times EMF times 1 minus e to the negative t, where that t right there is the same as that t there, how much time has elapsed, and then over RC, which is called our time constant of the circuit, and it's supposed to be a tau. That doesn't look like a tau. So it's a tau, and it's a time circuit, or the time constant of the circuit. All right, and then C times E is going to be the final charge on the capacitor, because as RC goes up, this whole thing right here is just going to keep decreasing, and it's going to end up just, or not decreasing, but this is going to decrease, and this is going to get closer and closer to 1. So as time goes up, because remember, this is 1 over E to the T over tau. So as T gets bigger, E gets bigger, this term over here is going to go to 0 as time goes on, and we're left with just CE times 1, and that would be fully charged. Now, if you know anything about exponential equations, they actually asymptote. They never actually get to there. We get pretty close, pretty much for practical purposes, the current stops, but mathematically speaking, we're going to say that it basically, we just keep getting closer and closer to the final total charge without ever getting completely there. All right, and you can see that here in this picture, showing you the charge on it as time t goes. So as you can see, we start off with the maximum amount of charge filling up on there, because remember, current is charge per time, and that means that's the slope of this line. So here we have the steepest slope. That's the biggest I. So that's I naught initially. It's really high, and then as we move up, you see the current being the slope of this line, right? Charge divided by time, which is slope here, is going to just start getting smaller and smaller, right? And so I naught is bigger than I1, which is bigger than I2, and it's just going to keep getting smaller and smaller and closer to 0, and then the total charge on it is going to max out at C times E. Okay? All right. It can also be shown in the opposite way, that the current has a related behavior. It's like this. It's essentially if you're a calculus person, it's the derivative of that previous thing, but it's the rate of change of that. And as we saw back here, we start with a high current, and then we go lower and lower and lower like that. And this graph shows us we start with a very high current up here, and then it just keeps getting lower and lower and lower and starts approaching 0 as the capacitor gets filled up. All right, and there's this equation here that'll tell you about what that is. But anyway, it's also just the derivative of the other one. But notice that, this charge grows, current decreases, which also means that these circuits, these capacitors, they're not ohmic. You don't want to be applying Ohm's law to these capacitors, because when you first flip on a switch, the voltage drop across the capacitor is 0, right? But it has a maximum current. So if you try to apply V equals IR, we're saying this is 0, but we're saying that's very big. So it kind of works that way. But then as the voltage raises, the current actually drops like that. And so it's not quite working out to try and use that on there. So don't treat them as ohmic things. Don't apply Ohm's law to these capacitors. So we talked before, I maybe should move that question back here, about the ammeter. So it's a device for measuring current. The voltmeter measures voltage. The current in the circuit, in order to measure it, it has to flow through the ammeter. So when you connect up an ammeter to measure current, you want to put it in series with whatever you're trying to measure the current through. So here, this is in series. Every bit of current that goes through this circuit has to go through that ammeter. So this would tell us the total current through the whole circuit. If we put the ammeter right here, it would tell us the total current just through this resistor, through this line right here. Okay, so we can do something like that. In practice, this is rarely done because it's very easy to break your ammeters, especially if you have like a digital one. Unless you're certain the current is going to be low, quite often you try doing this and you end up breaking the ammeter. It'll burn out the fuse or something like that. So you don't usually want to do that, because in order for this to not affect the circuit when you put it in series, because it has an internal resistance. You want it to be as small as possible. All right, that way it doesn't add much on to the rest of the circuit that it's in series with, because if it's in series and has resistor, it adds the resistance. So you want that to have as tiny, tiny, tiny resistance as possible so that it doesn't really affect the circuit. But again, this is not something you typically want to do. What you typically want to do is measure with a voltmeter and then use Ohm's law to calculate what the current would be. That tends to be a more often done practice until you get really good at it and you're sure you're not going to blow up your ammeter. Voltmeters, on the other hand, though, they need to measure voltage the same. So you have to put them in parallel, because things in parallel have the same voltage. They don't have the same current. Back here, if we wanted the total current through the circuit, we had to put this in series with the circuit to get the total current. If we wanted the current through R, right here, we had to put it in series with R so that the current through each of them is the same. That's what series is. Parallel, however, they have the same voltage. So you're actually like reading the voltage drop across this resistor. So the voltage drop across this will be the same as the voltage drop across your voltmeter, and therefore it can read the same voltage. However, if you add a resistor in parallel, you end up reducing that resistance, because especially if this had zero resistance. If R equaled 0 for this, all the current would go this way and none would go through R anymore, and we would be changing our circuit. So instead, the practice here is to basically try and make R as great as possible, like it's infinity. And then what'll happen is none of the current will want to go that way, and you won't really affect the circuit. It'll all still just go through that one. And again, back here, we want the resistance of this to be 0, or as close to 0 as possible, and we want that one to be as large as possible so that none of the current wants to go through it, and it doesn't affect our circuit very much. All right, so here we've got an RC circuit below. It has an R of 1200 ohms and an EMF of 12 volts and a capacitance of 0.001 farads. Right after the switch is closed, as in B, what are I and Q? So this is right after the switch is closed. As soon as we close the switch, the capacitor is totally empty. So right after it's closed, this is 0. All right? If that is 0, it offers absolutely no resistance, which means all the current is flowing through there. So if we look at our answers, we could go through and calculate. You could do Ohm's law, apply this pure EMF, this 12 volt EMF, and apply it to just that 1200 ohm resistor, right? You could apply that, well, let me make that an E or an epsilon. That EMF, we could apply that to that 1200 volts and calculate it. But if you look at our answers, both of those are just 1 milliamp. So I'm pretty sure it's going to turn out to be 1 milliamp. And then the only thing we need to look at then is the total charge. So it can't be B, because B has the current being 0. And it can't be A, because A has the charge not being 0. And when we first close it, the charge has to be 0. So it has to be C. So we have maximum current, no charge. Okay? All right. Let's try the next one. The RC circuit below, same circuit as before, so same exact thing. It says, what are I and Q after the switch is closed? So a long time after the switch is closed, which means we've let it fully go and totally fill up the capacitor. If that is the case, this is going to have some charge Q, and it's going to be full, which means I, that current, is going to equal 0. If I is 0, then then there's only one answer. If I is 0, that's the only answer it can be, is that one right there. Because that's the only one where the current goes to 0. The voltage drop across R is going to be 0. It's all going to be across the capacitor, and there's going to be no charge going anymore. And again, we have a big voltage drop across the capacitor, but this time we have absolutely no current flowing because it's full. Okay? That's basically it then for chapter 21. You probably really want to go back and practice, find some of the problems in the book and in the practice problems and in the mastering that help you practice with these breaking down the circuits and then using Ohm's law like we did, and also ones that used Kirchhoff's rules, the loop rule and the node rule to go through and solve these. Just make sure you understand a lot of these kind of things, how to use the power equations, how to add resistors and get the equivalent resistors, how to add capacitors to get their equivalent capacitors or capacitance, the junction rule, the loop rule, there's the adding of the capacitors, and then charging and discharging capacitors in RC circuits when there's a resistor present, like that. Okay, I think that's about it. Hope this made some sense. If not, let me know if there's something that needs further clarification. All right, thanks.